So I just want to discuss about question number 8 in B set. He says that there is a transformer which is connected in star and delta, and the voltage ratio of this transformer is 400 on star side and 33,000 on the delta side. He is given you the CT ratio on the star side as 1000 by 5 and is asking you to find out what is the CT ratio on the delta side. So as you know, for differential protection, if star delta is there, then CT secondary are connected in delta and star in this way, delta and star in this way. So there is one important thing that you have to notice about the CT ratio. See, what is CT ratio? CT ratio is nothing but the primary CT current by secondary CT current. Primary CT current by secondary CT current. So when you are mapping the transformer currents to the CT, the primary CT corresponds to the line current of the transformer, and secondary CT currents corresponds to the phase current of the secondary connection. Understood? Because in the primary side, where you can face the CT, where you can place the CT, you will place it in the line but not inside the phase winding, isn't it? Similarly, you see here, will you place CT in the phase winding? No, we will place the CT in the line winding. So that means, and you're connecting the primary of the CT in the line, whereas the secondary is becoming a part of the phase. So the current ratio of CT represents the top one, that is I1 represents the line current of the main transformer, I2 represents the phase current in the CT winding, CT connection. Understood? So from this I can understand that 1000 by 5 is given on this side, means the line current here is 1000 amperes, then the phase current in the delta will be 5 amperes. What will be that? Line current is 1000 and phase will be 5. If phase is 5, what will be the current in the circulating pilot wire? Pilot wire current will be 5 root 3. Now on the star side of the CT connection, what is the phase current in this star side? That is also 5 root 3, because in star, line and phase are both are the same. Understood? So if 1000 is flowing in line of the primary side, I want to find out how much current will be flowing on the line of the secondary side. So that I can directly find out by this relation, root 3 VL1 IL1, which is nothing but the volt amperes on the primary side will be equal to VL2 into IL2, as simple as that. So root 3 get cancel out, and from this I can write I line 2 will be equal to I line 1 into V line 1 by V line 2. So what is I line 1? Line current in the primary side is 1000 and line 1 voltage is 400 divided by this is 33,000. So 1000 get cancel. You will get I line 2 will be how much? 400 by 33 amperes. So this is the line current here. How much? 400 by 33 is the line current flowing in this way. So I will find out what is the CT ratio. CT ratio will be primary side line current, that is 400 by 33 divided by the secondary side phase current, that is 5 root 3. So 5 and 80s will go. You will get CT ratio will be 80 by 33 into root 3. Sir, but the options are not matching. How can we do? We will try to go for little bit approximations. So we will approximate by rationalizing the denominator. When you rationalize the denominator, then you will get 80 root 3 divided by 33 into 3, that will be 99. 33 into 3, that will be 99. This will be the final ratio. So if I will try to find out what is 80 into root 3. 80 into root 3 will be approximately. So you just want to find 80 into root 3, means let us say I am taking 80 into 1.7. It may be 1.73. Just take 1.7. So 80 into 1.7 will be something around 136. So let's just substitute the values. 136 by 99. 99 I will approximate to 100. So 136 by 100 will be approximately 1.36, something like this. This is approximate value. So for example, we will do trial and error. Take option A. Option A says that it is 7 by 5. So if you solve 7 by 5, 5 ones 1.4 you will be getting. So option A is 1.4 and what you got is 1.36. Here you have taken high. So if you reduce the value to 99, this value will be going somewhere on the top and it will be approximately equal to 1.7. From this I can directly tell 7 by 5 is the directly right answer. If you are having a calculator, then that is a different issue. Because you are not having calculator, just go for this kind of an approximations. Then you will get exactly the answer is 7 by 5 only. To arrive at this 7/5, we have done some approximate calculations like this. So option A is the right answer for this question. So here is the 11th question. I mean, in terms of set B. So set B 11 and A 27, C 56 and D 39. This is the question. And here in this question he has given you the ABCD parameter values. And he says that what should be the value of inductance that should be inductive shunt reactor that should be connected for compensating the Ferranti effect. So before understanding the Ferranti effect, or what do you mean by Ferranti effect before getting into the solution? The Ferranti effect is that effect which occurs when this transmission line is at low load or light loaded conditions. I mean, no load or light loaded conditions means, let us say to this transmission line, here is the generator, there is a transmission line which is having impedance and as well as the admittance. Why? Because he has given you the value of B and he has given you the value of C. So B is nothing but the transfer impedance, C is nothing but the admittance of the circuit. That means there is capacitance as well as inductance in the circuit, I mean impedance in the circuit. So this is the transmission line and there is a switch which is connecting load to the transmission line. So when I open the switch, that means the transmission line or the power system is under no load condition, and under no load conditions only you will have the Ferranti effect. And another important thing is Ferranti effect occurs under no load condition, that is okay, or light load conditions also okay. It occurs only in medium and long transmission lines. Why? Because while modeling a transmission line, only for medium and long transmission lines we will represent a capacitance, whereas for a short transmission line there is no considerable amount of capacitance. Therefore Ferranti effect is not defined for short transmission lines, but for a long transmission line and medium transmission line it is defined. Okay, next, any transmission line can be defined by using ABCD parameters, and these equations are very popular to you. Now I am telling that Ferranti effect will occur when the system is under no load or light load conditions. Let us say no load. No load means what? Receiving end current will be equal to 0. So if I substitute receiving end currents equal to 0 in this equation, what I am left over with? Vs will be equal to AVR. Vs is equal to AVR. See, if Vs is equal to AVR, if I want to find out what is the value of VR, VR will be equal to how much? Vs by A. How much it is? Vs by A. Now if you look at the value of A, what is the value of 8? 0.8. That means, can you tell me VR will be greater than Vs or not? Yes, absolutely. So VR will be greater than Vs. VR will be greater than Vs. So this is the example, or this is the representation, or this is the proof that in a transmission line Ferranti effect exists under no load condition. Sir, but how this is kind of analysis is made? How can you say like that? Why? Because the value of A is less than 1. If the value of A is less than 1, then definitely from this equation VR will be more than Vs. That is okay. So on what factors does the value of A depend on? So A value is basically directly proportional to the length of the line. If the length of the line increases, what happens? A will be decreasing. I can say it is inversely proportional. It is inversely proportional to the length of the line. So for higher long length of a transmission line, the value of A will be decreasing. If the length of the transmission line is increasing, means that means the capacitance in the transmission line is increasing. The capacitance in the transmission line is increasing means automatically the reactive power injected in the transmission line is increasing. That ultimately leads to Ferranti effect under no load condition. So that is one analysis that I want to make clear here. See, because I am primarily intended for those students who are below average. If somebody who is watching this video is more than average or who is a bright student, as I am suggesting, you may directly skip the videos or you may directly put it in fast forward mode and watch. But the student who want to learn from this question paper, you please stay with my pace and I hope you will be understanding all the things. But who are here just to know the key, I am suggesting you to just fast forward and find out what is the answer. Why? Because I am making these videos for a ordinary student or common student who is a bottom level student who is ready to learn from the mistakes he has made in this paper and he is ready to correct them in the next. So that is the reason why I am going in-depth analysis for each question. As you have seen the first part of the video, for 10 questions only I have made a video of 50 minutes. So I am going very depth because I am even touching all the connected areas for that from that particular topic. With this, it will be a kind of a revision for your entire syllabus. At the same time, if there is anything that you have untouched, will be also touched, and you will be very well prepared for the next upcoming EPDCL or SPDCL examination. Okay, so please bear with me. So one conclusion over here is Ferranti effect occurs on no load and in a transmission line, like I was telling. That means when the length of the line is increasing, the value of A will be decreasing, receiving end voltage is increasing. That means a Ferranti effect is occurring. And what does it basically signify? Rise in voltage signifies that, see, in a transmission line, basically there is a two types of power flow, that is active power and reactive power. So there will be active power generation and reactive power demand. Reactive power generation and reactive power demand. Tell me where the reactive power will be generated in a transmission line or in a power system. Reactive power will be generated in the generator, because our generators are overexcited generators. Alternator, when it is overexcited, it will deliver lagging reactive power. I can say reactive power is delivered. And another source of reactive power is line capacitance. Okay, capacitance in the line. Which capacitance is there here? This capacitor will also generate the reactive power. And reactive power demand is nothing but reactive power consumption. So who will consume the reactive power? Load itself will consume the reactive power, because 70% of the load in the transmission line or on the power system is a RL load only. RL load is the maximum load. That means I can say inductive load is the maximum load that is connected in a power system. So as I was constantly telling in our crash course or in my videos which I am uploading on YouTube, when reactive power generation is equal to the reactive power demand, that means the voltage of the system remains constant, or strictly telling, the receiving end voltage remains constant. But if reactive power generation is more than reactive power demand, the receiving end voltage will rise. That means excessive reactive power in the system. I can model reactive power as a salt in your body. Reactive power is like salt in the body. If you are having reactive power in the system, enough reactive power in the system, the voltage in the system will be maintained enough. See, that is what we do. Whenever voltage at any particular bus or substation falls, what do? Generally, we will connect capacitors. What is a capacitor? Source of reactive power. That means you are injecting reactive power means what? You are improving the voltage. That is what reactive power management means. See, voltage is nothing but electric pressure, isn't it? It is the pressure of electric current, and it is similar to blood pressure in human body. And blood pressure in human body is dominated by which element? Sodium, which is salt. If more salt is there in the body, more BP, more voltage. That means more reactive power in the system, more voltage. Like that we can understand. So since at the transmission line under no load condition, reactive power is generated by the voltage source, or I can say the generator, and line capacitance. You forget about this fellow. The capacitance will be more dominating in the transmission lines. So what happens? Excessive reactive power is injected in the system. But who will consume the reactive power? Load will consume the reactive power. But you have opened the switch. Where will the reactive power will go? It will simply stay in the line. So as a result, what happens? The receiving end voltage will keep on rising. So now what should you do? You should have somebody who will consume the salt. Because there is excessive reactive power generation at no load condition, what I have to do at receiving end? So this is only the receiving end now. What I will do at receiving end is, I will connect a load, or I can say a reactor. This is called as the shunt reactor compensation. What is this? Shunt reactor compensation. Shunt reactor compensation. Because you don't want to switch on the load, whatever may be the reason, but at the same time you don't want the voltage to go beyond. So I am connecting some other load or a reactor, which is an inductor, which will consume the reactive power. So this is called as shunt reactor compensation for Ferranti effect or under no load condition, or I can say when the reactive power in the line is excess. Understood? So what should be the value of this shunt reactor? So if I am having shunt reactor, it is connected at the receiving end. So the current drawn by the shunt reactor itself will be the IR, receiving end current. So what is the main intention in doing shunt reactor compensation? Means we will try to equalize the receiving end voltage and sending end voltage. Because sending end voltage is less, I will make VR is equal to Vs or Vs is equal to VR. So just take this equation. In this equation, put the values. I will put VR is equal to AVR plus BIR. Now I want to find out what is the reactance that is connected at the receiving end. So the voltage across the shunt reactor, let us say shunt reactor will have some reactance XSH. So if this is the reactance of the shunt reactance of the shunt reactor, what will be, it can be defined, it will be defined equal to VR by R, isn't it? Because this is the only element connected on the receiving end. So from this, if I can find this ratio VR by R, then I will get what is the shunt reactor required. So from this, you see, I am taking VR common. So VR will be 1 minus A is equal to BIR. So from this, I can write VR by IR, which is nothing but the shunt reactance to be connected for Ferranti effect will be equal to B by 1 minus A. So just by using the ABCD parameters, you can estimate how much value of shunt reactance to be connected at receiving end, so that you can neutralize the Ferranti effect. So the question is now very easy now. Now you only tell me what is the amount of reactance to be connected. So that will be equal to B by 1 minus A. And what is the B given in the question? 100. And what is 1 minus A? 1 minus 0.8 is 0.2. And what will this fellow will be equal to? This will be equal to 100 by 2 into 10, isn't it? So 2 ones and 5s, this will be equal to 500 ohms. So 500 ohms is the right answer for this question, which is option number C. Option C is the right answer for this question. So now we will discuss question number 12 in B set, and they are the question numbers in other sets. So he has given incremental cost of two generators, IC1 and IC2. You have to please keep in mind IC1 and IC2, incremental cost. Generally people are habituated, when you are giving some cost function, you have to differentiate with respect to P, and then you see when he says that only C1 or C2, then you have to differentiate that C1 with respect to P1, say like this, and that will be the incremental cost of first generator, IC1, or I can say, or this is also equal to lambda, Lagrangian operator. Understood? So that means he has directly given you the lambda value. So whatever IC1 or IC2 is given is nothing but the lambda only. Now he says that this generator system or these two generators have to be operated at economical cost. So when the generator will operate in economic condition, when the incremental cost of both the generators will be equal, then the generators will operate under economic conditions, and under that condition they both have to share a load of 250 megawatts. So what is the economic load sharing by generator 1 and generator 2 is asking. So he has given everything directly in the question only. So what we have to do, just equate these two fellows, then you will get the values of P1, PG1 and PG2. So he already given that PG1 plus PG2 must share this much load. From this I will write down PG1 equals to 250 minus PG2. So keep this as an equation which will helpfully here. So IC1 will be equal to IC2, that means 25 plus 0.2 PG1 equals to 32 plus 0.2 PG2. So already you know PG1 is equal to 250 minus PG2. So from this I can write down 0.2 PG1 can be written as 250 minus PG2. That will be equal to 25. I am taking that side. 32 minus 25. What will that equal to? That will be equals to 7. 7 plus 0.2 PG2. So if I solve this, I will get 0.2 into 250 will be equal to 50 minus 0.2 Pg2, and if I get this one also here, I will get minus 0.2 Pg2 equals to 7. From this I can write 0.4 Pg2 equals to 50 minus 7 is 43. Pg2 will be equal to 43 by 0.4. I can write 4 by 10 also. So 4 ones and 4 2.5. So 43 into 2.5, if you do 107.5 megawatts. So if Pg2 is 107.5 megawatt, you can directly find out what is Pg1. So Pg1 will be 142.5 megawatts. Pg1 will be 142.5 megawatts. So if you look at options, no options will have these answers. And if you look at option A closely, it has some printing mistakes. For that thing we can conclude. So even if you check the preliminary key, he must have given option A only correct answer for this question. But basically there is some printing mistake in option A. He has given 140.25. It should be 142.5. So in this way he has given wrong. So anybody if have attempted this question, we will get full marks basically, because his typing was wrong. Next 13th question, he says that there are two three-phase transmission line which is 1.6 kilometers long, 33 kV overhead line, and they are in horizontal formation. Horizontal formation for a three-phase line means this is the horizontal formation. He says that distance between the centers is how much? Distance between the centers is 762 mm. Is mm. He is asking to find out what is the effective diameter of the system. That is nothing but he is asking to find out what is GMD. So what is GMD? Basically, let us say the distance between two centers is D. So we are supposed to find the GMD of this system. So what will be the GMD defined as? GMD is nothing but the geometric mean of all the three distances. How many distances are there between the conductors? There is one distance, another distance, and there will be another distance between these two conductors, isn't it? 2D. So total three distances are there. I am taking the geometric mean. So that will be D into 2D. So that will come out to be 1.26 D. That is going to be the GMD. So what is the D given here? D is nothing but the distance between the centers. So that is 762 into 1.26, or I can say 1.25 approximately. So if you are supposed to do that, then you will get 960 mm as the answer. And that is the required GMD what is asking in the question, and that is option C. So for this question, option C is the right answer. Next, the question number 14, which is 14 in B, 30, 15 and 35 respectively in other series. He is telling that there is a large power system which is represented by some Thevenin equivalent, it seems. So Thevenin equivalent is having some ETH and ZTH, and he is given those values. He is telling that if a shunt capacitor bank is connected to raise the bus voltage to 1 per unit, MVR rating of the capacitor bank is. So if I am going to draw the system diagram, then you are going to have a voltage source which is ETH, okay, and it is connected to some infinity bus bar through some ZTH or some reactance. So this is the bus bar, and ZTH value here it is given as how much? J 0.25 per unit, because in the question he has mentioned that 0.25 at an angle 90 degrees is the ZTH. If this is ZTH, that is 90 degrees can be written as J 0.25, which is simply nothing but I can write XTH. Both are the same. So he says that the generator voltage is 0.9 per unit at an angle 0 degrees, and he says that you have to raise the bus voltage, this bus voltage to 1 per unit, but you are not known the angle of this bus. And how are you going to raise the voltage of this bus? By connecting a capacitor at this bus. What I am going to do? I am going to connect a capacitor at this bus so that the bus voltage will be improved to 1 per unit. So let us say this bus is supplying some reactive power, let us say some QC. It is supplying some reactive power QC in order to raise the bus voltage to 1 per unit. So first I have to find out what is the value of delta. How I can find the value of delta? Now let us look at the power, active power transfer equation that will be given by EV by X sin delta, where E is the bus 1 voltage, V is the bus 2 voltage, and X is the transfer reactance, and delta is the angular difference between them, and P is the power transferred. Now if you look at this kind of an arrangement, what is the active power transferred? Active power transferring is equal to 0, because that is what he has given in the question indirectly. So if I substitute the values, that is 0 equal to E is 0.9 and V is 1 and X is how much? 0.25. So when you will get a sine equation equal to 0, when delta is equal to 0, isn't it? When delta itself is 0 degrees, then you will get this value. So then I can find out directly this is at an angle 0 degrees. This is at an angle 0 degrees. Or without actually having to solve this, I could have directly found the value of delta, because upon drawing this diagram, I've got a conclusion that there is no active power transferred between these two buses, and it is already known that always active power transfer from a high value of delta to low value of delta. So that is the direction of power flow. But if there is no active power transfer between these two buses, means these two buses are at the same angle, that means, so need not solve it actually. Next we will see what is the reactive power received on this bus number 2, let us say that is QR. So by looking at this, I can say the reactive power received from the source is same and opposite like reactive power which is supplied by the capacitor bank. So if I can find QR, if I take minus of that, then I will get what is the reactive power supplied by the particular capacitor. That is what required MVR supplied by the capacitor bank is asking you. So what will be the formula for QR? So QR is given by this formula, that is receiving end voltage by X into E cos delta minus V. Substitute the values, 1 by 0.25 into 0.9, cos 0 will be 1 and V is 1. So this will be equal to 4 times 0.9 minus 1 is minus. So you got Q as minus 0.4 per unit. If QR is 0.4 per unit, what is the capacity of the, what will be the per unit MVR supplied by the capacitor bank? Minus of this one, that is 0.4 per unit. Now you got the per unit capacity of the capacitor bank. Now if you are supposed to find what is the actual value, so actual value will be equal to the per unit value multiplied by the base. What is base is given in the question as 100 MVAR is the base. So 100 into 0.4 is 40 MVAR, which is option number D. So option D is the right answer for this kind of questions like this. Next is question number 15 as per set B. In this question he says that a transmission line has equal voltages at two ends. So these are the two ends. Let us say all of them are the same value of voltage. Let us say this 1 per unit, and here also voltage is 1 per unit. And it is maintained constant by two sources. That means let us say there are two generators like this which are maintaining this constant voltage. Let us say this is V1 and this is V2. A third source is to be provided to maintain constant voltage equal to the end voltage either at the midpoint of the lines or at 75% of the distance from the sending end. So first case is telling that you are providing another source such that let us say this voltage is V3, that is also equal to these both points voltages. When you are going to have like this, when you are going to have a situation like this, that means if you are going to draw the vectors, if let us say this is V1 and let us say this is V2, both of them vectors are of the same magnitude, but there will be an angle between them called as delta. This thing we all are aware. Now you are going to introduce an vector which is exactly in midpoint of this line. So this angle delta is directly proportional to length of the line, isn't it? So if delta is exactly proportional to the length of the line, this vector will be located exactly at which point? In the center, isn't it? This will be V3 and the angle between V1 and V3 will be delta by 2 and V3 and V2 will be delta by 2. Now if you consider this is the active power flowing from bus 1 to 3 and same will be active power will be flowing from 3 to 2, isn't it? So what will be that active power equal to? I can say that will be equal to, let us say between V1 and V3, that will be 1 into 1 by what will be the transfer reactance connected between them? That will be 0.5 per unit, isn't it? If you consider the original reactance was 1, now it will become exactly half. 0.5 per unit into sine delta by 2 will be the power equation. Now he is asking you to find out what is the maximum power transfer. So maximum power transfer in the second case, or I can say in the second case according to the question it is case 1. In the first case let us say the power is some 1 per unit. Now it will become 1 by 0.5 per unit. 1 by how much? 0.5 per unit. This can also be written as 2 per unit. So power has been become double. Now in the next case he says that it is placed at 75% distance from the sending end. 75% of the distance from the sending end. Where will be 75%? Somewhere over here, let us say. So here you are maintaining V3 as 1 per unit. How much you are maintaining? 1 per unit. So this part of reactance will be 0.75 and this will be 0.25. Sir, like you told that when you are connecting like this side power transfer, this side power transfer will be the same. So I will take the same concept and I will proceed, then that is wrong. When you are coming across this kind of situation, that is when you are having same voltages but distance between the voltages are different, then the power transfer between longest length will be the actual power that is transferred. Why? Because practically you see, practically this is the large length of the line. According to this large length of the line, what is the power transfer in this section? Power transferred in this section will be equal to, or I can say maximum power transfer that is required in the third case, or I can say maximum power transfer. Maximum power transfer will be the voltages 1 into 1 by what will be 0.75. So let us say this much amount of maximum power is transferring. Now in this section, let us say what will be the maximum power transfer? 1 into 1 by 0.25. So this says 4 by 3 and this says 4, isn't it? 4 per unit and 4 by 3 per unit. Now if you look at here, from here 4 by 3 amount of power is coming, and according to your equation here 4 per unit power is there. From where the bloody hell the other amount of power has come into picture. For more clear understanding, I will multiply this with 30 and this also with 30. This will become 120 per unit, and 30 and 10 get cancelled. You will get 40 per unit. So that means from this source side you are getting how much power? 40 per unit of active power is coming from the source. Now if you are telling that this power also must be the same, when you are calculating it, how much power you are getting? 120. So when you are transferring 40, from where the hell 120 is coming in the picture? Because this particular source which is maintaining here, it is just supplying reactive power. This is nothing but this is a STATCOM or a FACTS. This is a FACTS device basically. FACTS device is just a voltage source. It will just inject reactive power and try to maintain the voltage, but it will not supply any active power. It will not absorb any active power. It only deals with the reactive power, and reactive power is nowhere concerned in our active power equation. So from this, even though the capacity of this portion of the line is to carry 120 megawatts, but it will not carry 120 megawatts. It will just carry 40 megawatts only. Understood? That is the maximum capacity. But since 40 megawatts has been transferred, here also 40 megawatts will prevail in the circuit. Understood? So this will be your actual maximum power transfer in this case. So when you look at P3, that will be 1 by 0.75. So if you look at the ratio, it will be 1:2:1 by 0.75, which is option B here. So this question was asked in GATE 2000 year, GATE electrical 2000 here. Now as we go on solving the questions, you will understand that most of the questions are repeated from GATE and IES questions only. Now 16th question, as per set B, he has given 3 conductors or a stranded conductor. I can say this is a stranded conductor which are touching with each other, and these are the centers of the conductors, and the centers of the conductors, if you are joining them, it is forming an equilateral triangle. And what will be this distance will be equal to radius. This distance will be equal to radius. So I can say the distance between the centers will be how much? 2r. So the distance between the centers of the conductors will be 2r, 2r, 2r. Now he is asking you to find out what is the geometrical mean radius of this conductor. GMR you are supposed to find. So when you are supposed to find GMR, first take under root, and under root you place a number here. So that depends upon how many conductors are there. 3 conductors. So it will become cube to root. So when you are having this kind of an arrangement, basically when you join the centers of the conductors, when it forms a polygon, this kind of formula will be applicable. Now here polygon formed is a triangle. It may also form a rectangle or something else. So choose any one conductor. Let us say he is my friend, I am choosing this conductor. So what will be the self radius of this fellow? What will be the self GMR of this fellow? So self GMR of this fellow will be how much? R dash, isn't it? Because self GMR of a conductor is R dash. R dash means what? 0.7788 into R. So what is this 0.7788 come from? This comes actually from the derivation of internal inductance. So when you have internal inductance component, you will convert internal inductance and external inductance into one equation. There you will get this term over here that will be obtained by doing this e power minus 1 by 4. There will be a term called e power minus 1 by 4 which will be equal to 0.7788. So that you will understand when you will watch my video of derivation of inductance. So this 0.7788 is nothing but e power minus 0.25. So I can write e power minus 0.25 into R is the self radius of this fellow. Next, try to find out what is the distance from this fellow to other conductors. From this conductor to this conductor, the distance is 2r. From this conductor to this conductor, the distance is 2r. That's it. Over. So, which is nothing but option A. Option A is the answer for the question. Next, question number 17. This is from Power Systems Generation Economics. He says that a consumer is consuming 600 kilowatts consumption per day. So, energy consumption per day is how much? 600 kilowatt hours. Next, he says that this fellow is having a load factor of 0.4. Now, he wants to increase the load factor to how much? 0.7 without increasing the maximum demand. What will be his new energy consumption, he is asking you. First, we will look at the first case. What is the load factor? In fact, I can define as load factor. He is given energy consumed per day. So, you have to take daily load factor. Daily load factor is nothing but energy consumed in a day divided by 24 hours in a day into maximum demand of the consumer. So from this you can find out what is maximum demand. Maximum demand will be energy consumed in a day, that is 600 kilowatt hour divided by 24 into load factor is how much? Initially 0.4, I can write it 4 by 10. And upon solving this, what I will get? Maximum demand will come out to be 62.5 megawatt or kilowatts. Okay, 62.5 kilowatts is the maximum demand for this consumer. Now he is asking you to find out what is the consumption to maintain load factor of 0.7 without changing the maximum demand. As simple as that. So I can write EC2 will be equal to load factor 2 into 24 hours into maximum demand. That's it. So what is the load factor 2? 0.7. So I'll write 7 by 10 into 24 into what is the maximum demand? 62.5. So 62.5 I will also write it like this, 250 by 4. So after solving this, you will get this is 6, 10 get cancelled out, and upon doing this you will get the answer as 1050 kilowatt hours, and which is option number C. Option C is the right answer for this question. Next, question number 18. For an SCR during turn on and turn off, quantities responsible respectively are, that is directly option C. During turn on process, the current which will decide whether the device is turn on or not is called as latching current. If the device is said to be turn on, if the anode to cathode current is greater than latching current, then only turn on is confirmed. And next, regarding the turn off related current is IH, holding current. If the anode to cathode current is less than the holding current, then the device is confirmed turn off. So which is option C. Next, 19th question. He says that a particular power electronic converter develops a symmetrical output voltage from pi by 6 radians to pi radians. Let us say this is pi radians. So he says that it will have a waveform from pi by 6 to pi and 7 pi by 6 to 2 pi, and both of them are symmetrical. So symmetrical means this kind of a waveform. Understood? So this is a symmetrical waveform, and tell me which kind of a device will allow you to have control on both half cycles without changing the symmetrical. So that is simply nothing but a triac. In triac you are able to control both positive half cycle and negative half cycle. So this is option C, triac will be the right answer for this question. Next, question number 20. In this he is telling that there is a single phase midpoint full wave SCR converter. So single phase midpoint means you will have a center tap transformer, and the load will be connected between the center tap in this way. So for this kind of converters, what is the output voltage is asking you. So the output voltage equation will be Vm by pi 1 plus cos alpha. If alpha is equal to 0, then V0 will be equal to alpha 0, means this will be Vm by, cos alpha will be 1 plus 1 is 2. So you will get 2 Vm by pi for alpha is equal to 0. If alpha is pi by 2, cos pi by 2 is 0. So then you will get simply Vm by pi, which is nothing but option A here, given here. Option A is the right answer for this question. Thank you for watching.